So it works now. Oh my god. Why this happen? I'm sorry, I'm so sorry. Capture string output. Oh my god. Preview, where is the preview? Oh, no, yes, no, preview. Got it. Okay. Yeah, I just give up the word and use the preview to open the file, but I cannot edit it anymore. So yeah, let's start. It's a little bit strange, I think. No. Oh, all the formulas. I cannot see any formulas. What the heck? Oh, damn it. Okay, it works now. Okay, let's start. So, first of all, I need to introduce the wind mode matrix. Basically, for typical polynomial, we can write the form like this. But actually, we can also write it as the vector, a vector of coefficients, and multiply by the sequence of x. And for endpoints, so if we have endpoints, so there's no surprise. We can write it as the form of matrix. That's what a random mode matrix is. It's like that. So, so this matrix is very important, and in the inverse FFT, this matrix is very important for the proof. Mm, okay. So basically, this matrix is for each row is a point, and so we have n rows, then we have n points, and the right side is the vector of coefficients, and yeah. So basically, my idea is just want to tell you the endpoints can be represented as a matrix multiplied by a vector, and the right side is also a vector. Mm, so here we have here is about the inverse FFT. Mm, yeah, this is adapted from the lecture, and we can I will go through the proof of how to do the inverse FFT. Actually, it's not difficult at all, and it's just like it's nothing but a FFT, a typical FFT. But yeah, what FFT did is just try to get the right side by multiply the matrix and the coefficients. So I have some donations here. So for f is the value domain of the vector of value domain. So say we have endpoints, and the value of each one is the value domain, and the matrix m omega and m omega to the power of minus 1 is the wind mode matrix. So let's recall what FFT did um, to get what FFT did. The input is simply is is simply is a vector is a coefficient, and another one is omega, of course, the root of unity, and the result, the output, is the value domain. So FFT is just given a vector of coefficient, given a vector, and given a root of unit, it can return the value domain. It sounds like FFT is to multiply the matrix and the vector, but it can run n log n complexity. It's much better than n square. So for inverse FFT, what? I'm not seeing anything. It's not it's not clear or it's totally dark. Okay, so maybe it's about the internet. I will continue. Mhm. You can, yeah, if it's not clear, you can try to select uh, increase the resolution. Yeah, so FFT is just a function, and you give a vector of coefficient and give a root of nth root, and it can return the value domain. Basically, it did something like multiply a matrix with a vector. So for the inverse FFT, it's not difficult at all. It's just run the FFT again, but it's not on omega, but yeah, it's the inverse omega. So here is proof for the inverse FFT. In fact, it's very simple. Here is the one mode matrix multiplied by the coefficient, and we can get the result. Actually, actually for the FFT part, our goal is to get F, but in the inverse FFT, we have F and we want to get A. So here is a proof how to transform this formula to this formula. Transform the A to the right part, to the right side like that. Mm, so, so here's the proof, and it's very easy, I think, very clear, and we can simply multiply by the reverse of the matrix. So multiply by the reverse of M in the two sides. Here we go. This step is very simple, right? So, so this part is the identity matrix. So it goes to A, and the right part is like this, unchanged. And actually, the one-mode matrix has a very good property. The reverse of the one-mode matrix has the form of like this. So we just replace the the reverse of matrix M by the right side here. So we have this form. And yeah, do you think it's very is similar to the FFT? FFT is what? It's like it also do the matrix multiplied by a vector. Here is the matrix, and here is the vector. And omega to the power of -1 is also a root of it is also one of the root, right? So we just run FFT on this part. The vector becomes to F, and the omega becomes to its reverse. So we can calculate this part, and the output is also a vector, and just divided it by n, we can get the coefficients. So, so the conclusion is like inverse FFT is similar to FFT. It's just the core step is the proof. However, is we can just memorize the result. So it's nothing but a FFT. There is no inverse FFT actually. And yeah, I conclude some steps here to solve the polynomial multiplication. The first step is to get f1 and f2. F1 and f2 is like this one. The denotion is here. Basically, it's the value domain vector of n distinct points. And yeah, to get two of them, just run the iFFT on the coefficient, and to get the f, we just multiply the two vectors. And again, we do the run iFFT again. This step is called the inverse FFT. Actually, it's also a step of FFT. Yeah. So it seems like it's very easy, right? Very clear. Okay, here is the example. And some students think the example is not very, yeah, without much details. So I will give you a lot of details. Oh, I think the student mentioned, can we do an example to understand better? What do you mean by it's about these three steps or something else? Actually, we have two examples below. It's about the FFT and the inverse FFT. Okay, let's go to the example. So here is the polynomial, and I rewrite it here. It's 1 plus 0x. Cool, thank you. Yeah, here is the polynomial in the problem. And what we did is to split it to the even and odd part. The even is the 1 plus this one, yeah. So it's 1 plus x. The other side is 0 minus 0 minus x. And again, split this part again. The even is 1 and the odd is 1. 0 and minus 1 is clear, right? So for this part, it didn't contain the x anymore. So it's not related to the value of x. We just need to get the, so for any x, the result is the same. It's 1, 1, 0, negative 1. And for this part, we need to use two of yeah, this one and this one to get this one and this one. So we can recall the formula. The formula is like the previous, the even one plus omega multiplied by the odd one, and the second is the even minus omega multiplied by the odd. So yeah, so what is omega? Omega here. Omega is the negative one, but the first root, I mean, in the Wend mode matrix, here you can see is the power of 0, so all of them are 1. So negative 1, negative 1, the power of negative 1 to the power of 0 is 1. So it simply here is should be 1. Let me see, I can write something here. Oh, I found a way to edit it, to edit something by myself. Cool. Not bad. So here is the omega to the power of 0 equals to 1. So it should be negative 1 to the power of 0 is 1. So just 1 minus 1 0 1 plus 1 2. Yeah, the same for this part. And for this part, it should be careful because it not just use the first point. Here omega is the I, and the same. The power of 0 is always 1. But here is we have 4 points, so we need to use 2 of them. Yeah. So for this one and this one, we use the omega to the power of 0. That is the 1. So 2 plus minus 1. Yeah. 2 minus negative 1 is 3. And for this for two for this for the second and for the fourth, there should be we need to use the I. Omega equals to I. So it's 2 plus I times order. So it should be like this. Oh my god. Yeah. For this part is minus. So it's just a minus I. Is this clear? Yeah. I hope it makes sense. Are you following this part? I mean, the FFT example? If yes, I will go to the second example. Yes. Confusing people is the blue nice. Thank you. Blue nice, blue line. Oh, blue line. Yeah, the blue nice. Blue line. Because you can record the formula is always not what the butterfly. Yeah, the blue line our early result. The blue line is like we can record the formula. The formula is like the formula is always even plus omega times order and even minus omega times order. Yeah, it's just keep using these formulas. It's nothing very confusing, I think. The even, and actually I write the even and order, split the even and order in very details here. The even order. So here is the even order. For the first one is the even plus order. The second one is even minus order. For the first one, even plus order. For the third one, is even minus order. Yes. Thank you, guys. So the merge sort is, I think The FFT algorithm is very similar to the merge sort. We always got the result from previous one and merge the result to a new result. It's like that. A merge sort is very similar to the merge sort. Okay, let's go to the inverse FFT. Actually, it's nothing but to do the FFT again. It's almost the same. So okay, and also I will do the same thing. Here is the polynomial. It given the coefficient, but to make it clear, I write it as a polynomial. So here is the 5 plus 4 minus 1x minus x squared. Yeah, this one. And just like the previous example, I split it to the even order. The even is 5 minus x, and the order even order even order. Yeah. So what we do is do the same thing. Here, for this part, it doesn't contain any x, so just by the fill it by the coefficient. It's 5 minus 1, 4 minus 1, 4 minus 1, and for this part, the blue light, yeah, again, is just use the formula. It's the even plus order, even minus order. Yeah, because for this part, I think the difficult part is we decided to use the omega. Here the omega is equals to 1. Here the omega, not the omega. It's the first point in the Van der Waals matrix. The first point. It's always 1, right? So here I used the 1. Yeah, just do the same very simple calculation, and we can this result. And for this part, shouldn't they be using? Oh, oh yes. Oh, I think so. Here the omega should be minus I. Yeah. Yeah, you're right. I think it's a typo. Um, oh my god. I will change this. Yeah. It should be minus 1. But yeah, for this, okay. So here is minus I, because it's a inverse FFT. We need to use the omega to the yeah. Okay, I will go through the step and then view the message. So for this part, here is the difficult part. For this one, we need to use the even and order. Even is just plus 1. 4 plus 8 is 12, no problem. And here is negative 4, no problem. And for this part, actually, we need to use the minus 1. So it's 6. Okay. So it's For the second, there should be 6 plus minus I times order. The order part is 2I. So it turns out it should be, or be what? What? Is this 4? Uh-huh. I thought you wrote at omega because blue line has a minus 1, 2, then... Oof. Oh, I think there is a problem here. Why it should turns out it should be it should be 8, right? Omega 1 equals to I1. Then because I thought this one should be the even. Oh, oh, it should be the even part minus. What the problem is? Then there is needed 2 times. I thought here should be 8, but previous I didn't get this confusion. I didn't get confused before. I don't know why. Yeah. I am. I think it should. I thought it should be the even part, plus the omega, plus the omega, plus the omega times the order part. Did he fix 2 i's in the middle? Two i's. Where is the 2 i? Here. Yeah, here is 2 i's. Uh, 4. A minus 1 is 2 plus, and to the right of OS. So here should be negative 2i, right? Is this correct? So here, oh yeah, yeah. Here is a typo. Yeah. Yeah, here should be negative 2, negative 2. So, so the procedure is right. Is the second part is the even one, the even plus omega times the order. So here should be 4, and the fourth, I mean fourth should be a minus the even part minus negative I. That is the omega, and times 2i. It should be 8. Oh, thanks a lot. I didn't find the typo. I just ignored it. I thought, oh my god. So here it works. So the idea is just uh, tell you the formula. Where the formula? It's a even even plus omega, even plus omega times order, even plus omega times order. Here is 4. Yeah. Okay. Yeah, actually, this picture is a screenshot from the Queens. So here should be negative 2, and everything works fine. Otherwise, I will get very frustrated. Thank you a lot. Okay. So here is the inverse FFT. You can see we did just rerun the FFT algorithm, but the omega should be omega is I, but the omega, the inverse of omega should be minus I. Yeah, it's nothing but the FFT. Nope, nope, nope. So all of you are clear for this part, for this example? I think the detail is just to split the polynomial to even part and odd part and do it again for the sub problem. Here is the detail is all the detail is about this. And after that, you just use the formula that is even plus order, even minus order. Yeah, of course, time order times omega, like that. So if you are clear about this, I will go to next step. So are you guys all clear? No problems, no questions? No questions anymore. Yeah, yeah. Cool, cool, cool. Oh, okay. If there's no questions, we'll go to the problem set. So for this part, we'll solve three problems. The 5, the 4, and the second one in the problem set 7. And here is the problem. I will give you, for the most part, yeah, okay. I will give you 1 minute to read the problem. I will take a break, take some water. Okay, let's resume. This problem is try to solve the multiplication by use the time complexity n log n. Actually, it's impossible. It's impossible to do that theoretically. Uh, mm, so 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 this part for this part, no problem. Yeah, if we can do it, of course we can just substitute the x by the 2, and we can get a times b. However, the problem is here. It just the a. Well, let's say what is a? A is the coefficient, right? Coefficient is a vector. B also the coefficients vector, and it just put the vector into inverse FFT. As I said before, inverse FFT is nothing but just a run FFT again. However, we can run FFT for any kind of vector. However, in iFFT, we expect the specific result, and we have the proof, and in the proof we have the valid domain vector. That's very important. Let's go to that part. Uh, Here we based on this. The proof started from here. Started from this equation. However, in the problem in that strategy, his f is not the valid domain. It's just a coefficient. Actually, a coefficient vector can be any vector, right? You can write it as anything. So it didn't work because the proof didn't. The logic is wrong. The start of the logic is wrong. We can run the inverse FFT, but we cannot expect the result if we didn't given the valid domain vector. So what should we pass to the iFFT? Yeah, it's just simply pass the Wend model matrix multiply by the coefficient vector yeah, coefficient, and the right part is what we needed to put in the iFFT as a parameter. It should be the valid domain vector. Let's say what we wrote before. Yeah, I wrote something like this. The input f is the valid domain of the nth root. In our algorithm, we just in the first we got it from the second step from previous FFT. However, here a and b is just a coefficient vectors. It's not the valid domain vector. And in the inverse FFT, we need the valid domain of n distinct point. From starting from there, we can inverse. We can do something inverse to get the coefficient. So also I have a comment here. We can run FFT on any input vector. Yeah, it's just an algorithm that didn't care. It doesn't care what was a parameter. It doesn't know the actual meaning. What is nothing in the statement of the program says coefficient vector that defined as function. So what is A? A is A0, A1, an-1 is like this, right? So A is the coefficient because A0 is just like the polynomial A0, A1, A2, A3. So A is the coefficient vector. Makes sense? And B is the thing. The coefficient is a base of a number, is a base of A. So the coefficient is still a coefficient, but the coefficient is a little bit specially because it only one or zero. What? It's only 0 or 1. It's binary. Confusion might be due to the define as bit. Yeah, it is. It's a bit of A. And in the strategy, the strategy regarded the number as a function, as a polynomial. And what is the coefficient of the polynomial? The coefficient of the polynomial is exactly the bits of the number. And it think we multiply by two numbers. It's just like we multiply by a polynomial and substitute x with 0 with 2, and so it's exactly the same as the binary represent of a number. Yeah, exactly. The function, the polynomial ax, use those bits to form a polynomial exactly. So the a is a coefficient vector. And another question is about the valid domain vector. Is I mean the valid domain. I mean two. If we have write something, I will write something. For x, for example, we have endpoints x0, y0, x1, y1. So I mean the y0, y1, y yeah. Here is the domain of the valid domain vector of those endpoints. I could take the inverse for real from I will finish the answer to that question. Yeah, here is what I refer to a valid domain vector. It's like you've given endpoints, and you need to find the corresponding value of the fx. So in our proof, the f here, the f is is the needed vector because it is, and the van mode matrix is just endpoints, and the f what someone. Oh my god, just wait a second. I believe the problem. Oh, another TA told me, uh, but why? Yeah, I didn't get an official solution for this problem. I just figured out by myself. Coefficient of C. But actually, uh, in the inverse FFT, the parameter should be the parameter. I mean, in the inverse FFT, the parameter should be f. That is not any given vector. It's not a randomly given vector. It's specifically for got from this equation. Coefficient of C. Yeah, the, the coefficient of C is the convolution of A and B. Yeah, no problem. Not valid. Yeah, the summation are only valid at a single point. Anyway, another TA told me, yeah, Yujie told me she has she disagreed with my solution, and yeah, I'm gonna discuss this with her, and yeah, no worries. I think do FFT. Oh, hmm. Okay. Doing FFTA minus omega will do. A Yeah, maybe UJ is right. Okay, I will go back to it, or UJ will discuss this problem in his session, in her session. Sorry. Okay, let's go to another problem. Yeah, hopefully UJ will take this problem in the next office hour. Oh, I'm sorry, because we didn't get an official solution. Okay, for the problem 4, um, give a list of given a list of value. This one. Show how to find the coefficient of p degree at most. Oh, so it's just the problem is just giving you n roots and find out the coefficient of the polynomial. Yeah, so the problem is very easy, I think. Yeah, because it's roots, so we can write the polynomial as a form of this. Just yeah, like this one. So yeah, actually you can see it's just the multiplication of n small polynomials. This one, this one, this one, and this one. However, I can do it better by using divide and conquer and divide it into two parts. The f1x, the f2x, the yeah, just divide it into two parts. So fx, yeah, I'm also very curious about that problem. Oh, okay, I see. Yeah. So fx is about is just the multiplication of the two polynomials, and for these two polynomials, we can use FFT to do it in all n log n time complexity. So the overall time complexity is like this one. We divided the problem into two parts, and the size is n divided by 2, and the cost is, for each step, the cost is at most n log n. Here is the FFT. So it turns out the result is n log n times log n. Yeah, that's what the problem asked. N log n square. It's simple. I think in the exam, the problem will be difficult than this one. Second, so for the second problem, and yeah, it's about given two polynomials, and this one, oh, it's just substitute the x by the bx, right? Substitute it by bx square, bx to the power of n. And my idea is very simple. Just to calculate those guys. Calculate bx power, it should be power of 0, power of 0, power of 1, power of 2, power of n. Yeah, just do it iteratively, and sum up the summation. And yeah, to save time, we can use FFT to do the multiplication. So let's analyze the time complexity. For each step, the degree will at most n square. because it at most the most should be bx to the power of n, and the degree of bx is n, so it's at most n square. So for each step, the cost should be just substitute the n by n square into the time complexity of FFT. Yeah, we got this. No surprise. And just do it n times. So just multiply it by n. It turns out the time complexity is n to the power of 3 and log n. Yeah, we're done. Let's go to this problem again. I thought it should be. I thought it's because just given. So for inverse FFT, if we given, yeah, it, A is the coefficient vector. No problem, I think. iFFT recall. So the for FFT convolution equals to FFT A by 2B. I think it's the same. There's no issue about the definition of A. Okay, I will talk. Yeah, for number like 5, the binary representation of 5 should be 1, 0, 1. Yeah, that's 4 plus 1, 1, 1. So the polynomial a equals to 1 plus 0 x squared. Here, this one is the last one here. Yeah, it's simply a binary representation. You just send me a message. If iFFT. Hold on. Okay, so Yujie told messaged me that uh, it's not about the A and B because the FFT is all about the matrix multiplication. So it's not about the definition of A and B. The the problem in the strategy should be should be we need to here is n square, but when we do the FFT back, we just multiply by n, not n square. So maybe here is a problem of the strategy. But anyway, I believe UJ will give you a better solution for this problem on Thursday. So yeah, let's go through the whole office hour. Basically, we do start from the theory of FFT. It represents the typical polynomial as the form of vector. And for endpoints, we have the matrix multiplied by a coefficient vector. And the inverse FFT. It is simple. The proof is simple, and the inverse FFT is just to do the FFT again. And the result for the examples, the key is to split the polynomial into the even part and odd part, and do from the left side. Use the formula of even plus omega times order, even minus omega times order. Use this equation to do those things. And in the inverse FFT example, the procedure is almost the same. And for this problem, Yujie will give you more details. For this problem, it's simple. Just use divide and conquer, and run FFT as a subroutine. So in the exam should be a lot of problems should be about run a typical algorithm for a given problem. This problem is also the same. Run FFT as a subroutine. So that's all for today. Thanks. Oh, thank you guys. And yeah, bye bye.